Today, let's discuss about the matrix representation in computer graphics. In computer graphics, matrices are the fundamental mathematical tool used to represent and manipulate objects in 2D and 3D space. This presentation will explore the power of the matrix representation, how it enables the core transformation of the translation, rotation, and translation. It represented by a matrix that shifts an object's position along x, y, and z axis. Rotation, described by a matrix that rotates an object around the x, y, or z axis by a specified angle. Scale, defined by a matrix that stretches an object along x, y, and z dimensions. Combining transforms, matrix can be multiplied to apply the multiple transformations. Coordinates. It represents points and vectors. Homogeneous coordinates extend the standard Cartesian coordinate system, allow for the unified representation of the points and vectors. Simplify the transformations. Homogeneous coordinates make easier to apply the complex transformation like scaling, rotation, and translation. Handle the perspective projection. Homogeneous coordinates are particularly useful for handling the perspective projection in 3D graphics. Multiplicative and translation terms for the two-dimensional geometric transformations into a single metric representation by expanding the 2 by 2 matrix representation to 3 by 3 matrices. For that, express all the transformation equations as matrix multiplication. To express the two-dimensional transformation as matrix multiplication, we can represent each Cartesian coordinate positions xy with the homogeneous coordinates xh by h, where x equal to xh by h and y equal to yh by h. For the two-dimensional geometric transformation, we can choose the homogeneous parameter h to be any non-zero value. We choose as h equal to 1. Each two-dimensional position is then represented with the homogeneous coordinates x, y, and 1. Are represented with three-element column vectors, and transformation operations are written as 3 by 3 matrices. For translation, we can write in the abbreviated form p dash equal to t of tx dy into p, where t of tx dy is the 3 by 3 translation matrix. The inverse of the translation matrix is obtained by replacing the translation parameters tx and ty with their negatives minus tx and minus dy. Transformation equation about the coordinate origins are as p dash equal to r of theta into p. The rotation transformation operator r of theta is 3 by 3 matrix with the rotation parameter theta. The inverse rotation matrix is obtained when theta is replaced with minus theta. Of homogeneous coordinates. Unified representation. Homogeneous coordinates provide a unified way to represent the points, vectors, and transformation, simplifying the underlying mathematics. Efficient computations. Matrix operations on the homogeneous coordinates can be effectively performed using linear algebra. Handling projections. Homogeneous coordinates enables the seamless handling of perspective projections. Versatility. The flexibility of homogeneous coordinates allows for the representation of a wide range of geometric transformation that makes them a fundamental tools in computer graphics. Applications. 2D graphics. Metric transformations are essential for 2D user interface, game development, and vector-based design. 3D graphics. Homogeneous coordinates and matrix transformation are fundamental to 3D computer graphics that enable realistic rendering and animation. 4D spacetime and future potentials.